Bevel gear is, the bevel gears have a conical form. If you take this this profile, it's a conical form, right? It's a conical, right? You can see, right? This is a conical shape, right? Conical shape. So the bevel gears have a conical form and can be used to transmit the rotational power through the shaft that are typically not always the 90-degree, but typically, yeah, at a angle of 90-degree to each other. But it can be a 120-degree also. Okay, but typically, normally, the angle, okay, the shaft of the angle at 90-degree, but it's not always. Okay, that's why they put typically. Okay, typically mean generally. Okay, then this bevel gear drive mainly classify into four classes. Okay, first one is a straight bevel gear. Okay, the straight bevel gears mean the teeth is a straight form. Okay, it's a straight, like a bevel gears. Okay, the bevel gears, the teeth cut is a straight. No, likewise the straight bevel gear mean the teeth cut is the straight. Okay, the another type of the bevel gear is a spiral bevel gear. The spiral bevel gear mean, the teeth is cut at angle. Have you seen? Okay, the teeth is cut at angle. So normally that type of the bevel gear is normally we say what? Spiral bevel gear, and this one is a straight bevel gear. Okay, then another type is a meter. Okay, meter bevel gear. Meter bevel gear mean the two gears, the pinion and gear have a same number of the teeth. Okay, for example, this, on the right side of the bevel gear, the teeth are not equal, right? For the pinion and gear, it's not equal, the teeth are. But for the meter bevel gear, always these two gear, the number of the teeth are same. Okay, then we call the meter bevel gear. Okay, so first one we see the straight bevel gear. Second one we looked at the spiral bevel gear. Third one is the meter bevel gear. And fourth one is a hypoid bevel gear. So what do you mean by the hypoid bevel gear? It's also look like a spiral, right? The spiral bevel gear, right? It's also look like a spiral bevel gear because the teeth are cut at the angle. But maybe it can be a straight also, straight bevel gear also. But why they put the hypoid bevel gear is, if you look at other gears, you see the center of the gears, okay, the center line of the gears meet at here perpendicularly, right? This one center coming like this. You see, if you look at this one, this center like this going, and this center going like is meeting at this point. Likewise, this one also center going like this, and this one also going like this, meet here. But when you come to here, you see this center line here and this center line, this one, right? It doesn't meet. That's why we call what? Hypoid bevel gear. Okay, but this one, meter gear also is met, right? But hypoid bevel gear mean the center is not perpendicular. It's not meeting at the perpendicular. Okay, so that's a difference between the straight bevel gear and spiral bevel gear and hypoid bevel gear. You mentioned here, you see here is the differential system, right? So there we use the the bevel gears. Okay, and also you see, if you look at the motor is fixed on here, but you have application on this direction. So this inside, sorry, this inside, there is a bevel gear drive in order to transfer the rotational motion into 90-degree angle. Okay. So maybe other application you can see in the the helicopter, on the helicopter transmissions, and the marine, also the marine, the turbine blade in the below also, maybe they use the high point bevel gears. Maybe they have a, the available power is available on the one area, but they need to transfer the power into the other direction or other area, or it's offset by the 50 centimeter or something. Then they supposed to use the high point gear drive. They cannot use the they can't use, sorry, they can't use what the spiral bevel gears or straight bevel gears. They're supposed to use the high point bevel gears because they are offset. The two shafts are offset, okay, by itself, because of the public, because of the application requirement. Maybe the two shafts are offset by some distance, so they have only option to use high point gear drive. Okay, so maybe in the automobile they don't have the restriction, but in other application, in many application, marine application, or helicopter application, or the construction equipment like excavators or something, they can use this kind of the bevel gears drive. Understand? So it's widely used, but the drawback of the this bevel gear drive is it's expensive to manufacture. It's expensive. It's not like spar gears or any helical gears you make. It's quite expensive to manufacture. That is a drawback. So that is a quite drawback, because the cost can be determine the factor whether we can use this bevel gears or other kind of the mechanism. Okay, so the cost to manufacture is a kind of the big factor when you come to the bevel gears. Okay, let's say if you want to replace your differential gear in the automobile, in your car, it's quite expensive. It's not like others, other equipment, other drive. It's quite expensive. It costs you an arm and a leg. Okay, so you have to be aware of those things. The forces acting upon the bevel gear drive. Okay, this is the gear, this is the pinion, right? This is the pinion bevel gear, this is the gear, bevel gear. Clear? So when it rotates, you know how the forces come in acting on this bevel gear. This is the, I am saying the all kind of the theory aspect behind the bevel, the forces acting upon the bevel gears. And when you rotate on a counterclockwise, you see the FR is a radial force, and this one is a perpendicular force, and this one is a tangent. FT mean the tangent force on this gear, on the gear bevel. Okay, then these forces, radial force and this axial force. Okay, this one radial force, axial force, and this one is a tangential force on the pinion gear. Okay, so these are the forces acting upon the bevel gears. Likewise, we look at the rack and pinion also. What are the forces acting on upon the rack and pinion? Likewise, bevel gears, these type of the forces acting upon. Okay, so likewise, if you use this basic formula, and you can come up with the velocity ratio Ng, the number of the teeth, okay, upon number of the pinion is given the velocity ratio. Okay, this is the velocity ratio we derive for this specific mechanism. Okay, bevel gear drive. Okay, so for example, you see when you two terms moves by the 8 teeth, how much is moved by the big gear? Only one turn by the 24 teeth. So this is the gear ratio 3 to 1. So the velocity ratio is given by the number of the teeth divided by number of the pinion. Okay, so this formula you have to remember for this bevel gear, because we are going to apply this one for the calculations. Okay, number of the gear over number of the teeth of the gear over number of the teeth of the pinion. And the law of the machine also we are going to derive for this machine. That's mean what is the effort? Fe mean the effort we have to make for the given load force. So this equation we have to derive for this bevel gear drive. Okay, come to this our apparatus. Okay, so this is our apparatus of the bevel gear. Okay students, what you are seeing is our bevel gear drive apparatus. Okay, so now I am going to explain all the individual parts of this apparatus. Okay, because before you are doing practical, you're supposed to know what all the components are. Okay, let's get started. Okay, you see here these two pulleys. Okay, this wheel, these two are pulleys. Okay, this pulley is attached to this shaft and this pulley is attached to this shaft. So there are two pulleys. Okay, then you see this small wheel, small gear. This one is called bevel pinion. The small gear is called what? Bevel pinion. The big gear is called what? Bevel wheel. Okay, this one is the bevel wheel and this one is the bevel pinion. Okay, then you see the wheel is attached to this blue shaft. So this shaft is called what? Wheel shaft. Likewise, you see this pinion is attached to this blue shaft. So this shaft is called pinion shaft. Understand? Then moving on to these black blocks. Okay, these are called what? Bearing block. Okay, these black ones are called what? Bearing block. You see there is a bearing inside this block. You see there's a bearing. Okay, that's why we call this one what? Bearing block. Then come on to the right side of the apparatus. You see here there is a 1 Newton self weight of what? Hanger. Okay, you see the self weight of this hanger is 1 Newton. Then moving on to this side, the front side of the apparatus also have another hanger, but this hanger self weight is 0.5 Newton. Okay, so you're supposed to familiar with these parts of the apparatus. Okay, unfortunately you can't touch this apparatus since it is the virtual practical. Okay, but I do my best to get the picture of this full apparatus. Okay students, now we are moving into the procedure part of our practical. Okay, so here I am going to explain how we are going to do this practical. Understand? Okay, what is the first steps you have to do? Use the calipers to measure the diameter of the cord pulleys. I already explained these two are pulleys, so we have to use the vernier caliper to measure these diameters. Okay, I already measured. This one is a 20 mm and this one also is 20 mm diameter of pulleys. Okay, that is our first steps of the procedure. Okay, we have to measure these two
pulleys. What is the second step? Apply a load W to the hanger attached to the larger gear. You know, this is the larger gear, no, the wheel. So the hanger is attached to the larger gear. We have to put the weight. Okay, but now I already consider this hanger have some self weight, no. So I consider, okay, now this side have a 1 Newton of the load. Okay, because I don't first reading I am going to do with the hanger self weight. Okay, so the larger gear side, what is the load? 1 Newton. Okay, then what we have to do? Then add weight to the hanger on a smaller gear. You know, the hanger, this is a smaller, this hanger is attached to the smaller gear side. Okay, then we have to add weights in order to move this larger gear side of the load. Okay, so now this side the load is a 1 Newton, but here is a 0.5 Newton, but still the 0.5 is not enough to lift this side of the hanger. So what we are going to do is we are going to add weights on the pinion side of the hanger. Okay, to see how much load or weights we have to add in order to just move the hanger that is attached to the larger gear. Okay, so I am going to place 0.1 Newton. Okay, but still not moving, so I am again going to add another 0.1 Newton. Okay, still it's not moving, so what I am going to do is I am going to take out this. Now it's moving. Okay, so what is the, you see, it's just about to move when I apply the 0.1 Newton. That's why it's just started to lift up. Okay, now it's moved. So what is the load side you have to apply in order to move this hanger that is attached to the larger side? Total, you see, here is a 0.5 and another you add 0.1 into 2, right? 0.1 Newton you added to the pinion side of the hanger. So total effort how much? 0.7 Newton. Okay, so likewise we have to repeat this procedure for this several loads in the larger gear side. Okay, now we are going to do the same procedure for another set of load. Okay, so we already done and get the value for the effort. You know how much effort needed to lift this 1 Newton load side? 0.7 Newton. Okay, so we already found that reading. Now we are going to add another 2 Newton in load side. Okay, another 2 Newton, and I am going to add the weights on the pinion side. Okay, and to see how much weight is needed to just to move this total 3 Newton of the load side. Okay, I am going to add 0.5 Newton. For 0.5 Newton not moving. Then I am again at another 0.5 Newton. Yes, it's moving. So the minimum value should be between 0.5 and 1 Newton, right? That's mean including this hanger weight 1 Newton, between 1 Newton and 1.5 Newton. So what I am going to do is I am going to add, I take out 0.5 Newton and I am going to add how much? Just see 0.2 whether it's move or not. Okay, you'll see. Not moving. I am going to add 0.1 Newton. Yes, it's moving. Okay, so what is the minimum value? Total minimum value. So total 0.5, 1 Newton and 1.2 and 1.3. So 1.3 Newton effort is needed to just to lift this 3 Newton of the load. Okay, so this is the second set of value. Likewise, we change the load side of the weight and get the minimum effort to lift this load side weight. Understand? So this is the procedure of this practical.
So, you know, the teeth on the small gears, I already calculated, that is 15, okay? And the teeth on the larger gear is a 45, okay? So you can find out the velocity ratio. Already there's a equation here. So you can use this by this, then you will get the velocity ratio. Clear? This is the load I applied for this practical. 1 Newton, 6 Newton, 11 Newton, and 16 Newton, and 21 Newton. Okay. So I will give you all the observation value for the in the effort section. Okay. For load 1 Newton, my effort is 0.7. And for a 6 Newton, 2.4. For 11 Newton, 4.1. For 16 Newton, 5.9. And for 21 Newton, 7.7. The mechanical advantage mean W over E, right? W is a load over effort. Clear? So that is our mechanical advantage. You can fill up this column, okay, by calculating this by this. Clear? Then you already know what is the velocity ratio for this bevel gear drive. Then you can fill up this column also, efficiency column, MA over VR. It's a similar, it's the same like what you did for the rack and pinion. Then ideal efficiency, EI, that is you fill up by F over, the load over velocity ratio. That also you fill up this column. Then effort of friction, that is E minus EI. This one also this column also you can fill up. Okay, the objective of this practical is alternately what? To find out the law of the machine. Okay, the law of this bevel gear drive. Okay, you have to find out what is the equation for that one. EA equal AF plus B. Okay, this is actual effort into the constant. A is a constant that you have to find out from this graph. And the F is a load, and plus B also another constant. Okay, this also you can find out from the graph. Okay, the value that intersect on the y-axis. Okay, that is the B, and that's one A. So from the graph you can find out the constants values of A and B. Okay, so alternately you can find out the law of the machine. Okay, the EA, the equation you will find out for this bevel gear drive.